Hello, my name is Sylvester Lawrence, and today I will be presenting my Six Sigma DMAIC project. This presentation demonstrates how the DMAIC methodology define, measure, analyze, improve, and control can be used to reduce defects, improve process capability, and generate significant cost savings in a manufacturing environment. Before discussing the project, let us first understand Six Sigma. Six Sigma is a data driven methodology used to reduce process variation and eliminate defects. It aims to achieve fewer than 3.4 defects per million opportunities, which represent world class quality performance. The methodology was first developed by Motorola in 1986 and later popularized by General Electric under Jack Welch. Today, Six Sigma has generated billions of dollars in savings worldwide and remain one of the most effective continuous improvement approaches. This table shows the relationship between Sigma level, DPMO, and process yield. At a 1 sigma level, the process produced over 690,000 defects per million opportunities, resulting in poor quality. As the sigma level increases, defects decreases dramatically. At 6 sigma, only 3.4 defects occur per million opportunities, achieving a process yield of 99.9997%. This illustrates why organizations strive to improve their Sigma level to enhance quality and customer satisfaction. Six Sigma is not only a quality improvement tool but also a business strategy. Organizations select projects based on their impact on cost reduction, quality improvement, and customer satisfaction. The DMAIC roadmap provides a structured framework for solving problems systematically and ensuring sustainable improvements. Six Sigma uses a hierarchical character-style belt system to denote varying levels of expertise and responsibility. So the first one is white belt, second one yellow belt, green belt, black belt, and the highest one is master black belt. There are two major Six Sigma methodologies. The MIC is used to improve existing processes by identifying problems, measuring performance, analyzing root causes, implementing improvements, and controlling the process. DMAV, DMADV, on the other hand, is used when designing new products or processes. It focuses on defining goals, measuring customer requirements, analyzing alternatives, designing solution, and verifying performance. Since this project focuses on improving an existing assembly process, the MAIC is the most suitable approach. The define phase establishes the foundation of the project. During this phase, we identify the problem, determine project goals, define scope, and understand customer requirements. The project charter serves as the roadmap for the project. The problem identified is an engine assembly line defect rate of 8%, while the target is only 2%. The objective is to reduce defects from 8% to 2% within 6 months. The project scope covers the welding station only, and the business justification includes annual savings of approximately 450,000 ringgit while improving customer satisfaction. The SIPOC diagram provides a high-level view of the process by identifying suppliers, inputs, process steps, outputs, and customers. These tools helps ensure that everyone understands the process boundaries before proceeding to data collection and analysis. In this step, the voice of the customer was collected using surveys, interviews, complaint analysis, focus groups, and direct observation. Customer requirements were translated into critical to quality characteristic or CTQs. For example, customers requested faster delivery, which was converted into a measurable CTQ target of the at least 98% on-time delivery within 2 days. The define phase revealed that the engine assembly line had a defect rate of 8.2%, causing 650,000 in annual rework costs and increasing customer complaints. The project goals is to reduce defects to 2% or less by June 2026, generating annual savings of at least 400,000 ringgit and improving delivery performance. This Gantt chart shows the 6 months project timeline. The project begins with defined activities in January, followed by measure, analyze, improve, and finally control. Toolgate reviews are conducted at the end of each phase to ensure project progress and readiness for next stage. The measure phase focuses on collecting accurate data and establishing the current performance baseline. The data collection plan identifies the key metric to be monitored, including defect count, cycle time, rework hours, scrap rate, and customer complaints. 30 days of baseline data were collected and analyzed using Excel and Minitab. Before analyzing data, we must verify that our measurement system is reliable. Gauge R&R was conducted to evaluate repeatability and reproducibility. The total gauge R&R value was 11%, which falls within the acceptable range, confirming that the measurement system is sustainable for analysis. Process capability was evaluated using CP and CPK. The process achieved a CP value of 0.79 and CPK value of 0.67. Since the target for capable process is generally above 1.33, these results indicate that the process is not capable and requires significant improvement. The estimated sigma level is approximately 2 sigma, corresponding to over 308,000 defects per million opportunities. The baseline results show a defect rate of 8.2%, a DPMO of 308,538 of CPK of 0.67 and a sigma level of approximately 2 sigma. These findings confirm the need for immediate improvement efforts. The Pareto chart applies the 80-20 principle to identify the most significant defect categories. The analysis shows that while defects and dimensional errors account for approximately 65% of all defects. Therefore, improvement efforts should focus primarily on these two defects categories. The analyze phase focuses on identifying the root causes responsible for poor processes performance. The fishbone diagram categorizes possible causes into 6 groups: man, machine, method, material, measurement, and environment. Several potential causes were identified, including unskilled operators, aging welding machine, lack of standard operating procedures, material inconsistency, measurement issues, and environmental condition. The 5 whys analysis was used to identify the true root cause. By repeatedly asking why defects occurred, we discovered that the main issue was the absence of a formal change management and document control system. As a result, SOPs were not updated after machine upgrades, leading to inconsistent work practices. Several statistical tests were conducted to validate the root causes. The result shows that machine type, shift differences, and SOP adherence significantly affect defect rates. All major tests produce p-value below 0.05, confirming statistically significant relationships. The priority matrix ranks root causes based on impact, frequency, and controllability. The highest priority issue was the lack of SOPs at workstation, followed by aging welding machines and inadequate charge management processes. This became the primary targets for improvements. Correlation analysis revealed that cycle time and machine age have the strongest relationship with defect rates. The strongest correlation observed was between cycle time and defects, with an R-square value of 0.72. This indicates that reducing cycle time variation could significantly reduce defects. The improved phase focuses on generating, selecting, and implementing solutions to address the root causes. Solutions were developed across three categories: process improvements, including standardizing SOPs and implementing visual instructions; machine improvements involve replacing aging welding machines and improving maintenance schedules. People focused solutions include operator training, certification programs, and quality champions. A weight decision matrix was used to evaluate all proposed solutions. SOP implementations received the highest score of 8.2 out of 10, making it the top priority. Operator training ranked second, followed by machine upgrades. The pilot study delivered significant improvements. Defect rate decreased from 8.2% to 2.8%, representing a 65.9% reduction. The PMO decreased by over 90%, while rework hours dropped by 68%. The result confirmed the effectiveness of the proposed solutions. These action plans outlines responsibilities, timelines, resources, and project status. Several activities, including SOP development, workstation posting, operator training, and quality checklists, have already been completed, while machine replacement and dashboard implementation are currently in progress. The financial analysis demonstrates the value of the project. The total investment requires was 117,000 ringgit, while annual benefits are estimated at 716 ringgit. This result in a return on investment of 512% and a payback period of approximately 2 months. The control phase ensures that improvements are sustained over time. A detailed control plan was developed for critical process parameters such as weld bit width, heat setting, bolt torque, and SOP compliance. The plan specifies targets, measurement method, monitoring frequency, and response action. Statistical process control charts are used to monitor process stability. The X-bar chart tracks weld bit width, while the P-chart monitors defect rates. These tools provide early warning signals when processes move out of control. To sustain improvements, daily monitoring, weekly reviews, monthly audits, and quarterly recognition programs were implemented. These activities help ensure continued compliance and encourage continuous improvements. The final dashboard summarizes project performance. Defect rate improved from 8.2% to 2.0%. The PMO reduced from 308,538 to 21,000. Sigma level improved from 2 sigma to 3.5 sigma, and annual savings reached 599,000. Although the CPK value of 1.28 is slightly below the target of 1.33. The overall project objectives were successfully achieved. Key success factors include cross-functional teamwork, data-driven decision-making, visual management, and pilot testing. Challenges include resistance to change, machine procurement delays, and initial data quality issues. The lesson learned can be replicated across other production lines. In summary, the DMAIC methodology successfully reduced defects and improved process capability. The define phase identified the problem, measure establish the baseline, analyze identified the root causes, improve implemented effective solutions, control ensure sustainability of the gain achieved. For further improvements, SOP deployment should be expanded to other production lines. Additional greenbelt training should be conducted, machine upgrades completed, and IoT-based monitoring system integrated. Long-term goals include achieving a Four Sigma level across all assembly lines and establishing a Six Sigma Center of Excellence. Thank you so much for your attention. This concludes my presentation on the Six Sigma DMIC project.